Let's take a look at a simple example of calling a function and returning from a function. This is a pretty simple code. We have here some location where we call myfunc, and in myfunc we have the ret instruction, which is supposed to go back here. We mostly care about what happens with the stack at this point. So let's begin with a drawing of the stack. It will be a bit different from the previous drawings because basically we want to draw the memory, but we want to draw it in a way that helps us to understand what happens with the stack. Instead of using separate bytes, I'm going to display the memory as an array of D words. This is what we actually see here. And we are going to assume that the address growth is in this direction. Down there we have bigger addresses, and on the top we have lower addresses. So the 0 is somewhere up there. This is the usual picture that you are going to see when you are going to talk to somebody else about the stack in the x86 architecture. This is how people usually picture the stack. Let's begin examining the code and see what happens to the stack. We assume that initially ESP points to some location in the stack, and this location determines which D words are occupied and which are not occupied. In this case, when ESP points here, the occupied part of the stack is from here to the bottom. Basically, we assume that from here all the way to the bottom, we have some D words which have some kind of meaning. They are already inside the stack. And this is the free space where we can add more D words. As an example, the next D word which is going to be pushed into the stack is going to be here. And the next one is going to be here. And so on. Let's see what happens when we call myfunc. What happened is that a return address was pushed into the stack and ESP was decreased by 4 to point to the new location. We can also see that the occupied space has increased by 4 bytes and the unoccupied space has decreased by 4 bytes. Let's see it again. Now we assume that some instructions happen here inside myfunc. Some work is done. I want to emphasize that this number that we can see here is the next instruction's address, which means that it is the address of the instruction here. We can't see the instruction here, but we assume that there is an instruction after a call. After the work inside the myfunc function is done, we get to the ret instruction. The ret instruction is supposed to look at the top of the stack, or in other formulation, to pop the last D word from the stack, and then use this address to return. It will actually jump to this address, which is the address of the next instruction. Basically, this is what is going to happen. I want to show it again. Now we understand what really happened. Call has kept the return address of the next instruction inside the stack, and ret just used this address to know where to return. Another important point to take from this picture is this. Note that this number is currently inside the unoccupied part of the stack. However, it is not deleted. There is no such thing as deleting a D word, because a D word always contains some value. It is pretty pointless, for example, to try to zero this number, because we don't really care about this number, as it is currently inside the unoccupied space of the stack. Even when we have finished with some values in the stack and they came back to the unoccupied space, they still have that value. The value was not deleted. Let's look at another example, this time of nested calling. This example is a bit more complex, but not that complicated. We can see here a call to func A, which in turn calls to two different functions, func B and func C. We can see those functions here. We can imagine this structure as a call graph, or maybe a call tree. We begin from start, which then calls to func A. Func A, in turn, calls to func B and func C. Let's see what happens when we run this code. This time I added some dummy addresses so we can better understand what we see inside the stack. Each address corresponds to the instruction to the right. So for example, call func A is located at this address. Let's begin and follow the stack. We begin by calling func A. The return address, which is this one, is going to be pushed into the stack. Next we are inside func A, and we are going to invoke the call instruction. So the return address, which is this address, is going to be pushed into the stack. Now we are inside func B. We first execute some work that should be done inside func B, and then we are going to return. The ret instruction is going to use the last D word on the stack as a return address. So we are going to return to this address, which is here. Next we call func C. The call instruction is going to keep this address as the return address in stack. Now we are inside func C. First we execute some work inside this function, and finally we get the ret instruction, which is going to use this value as the return address. Basically it is going to jump to this address, which is here. And this is exactly what happens. Now we are at the ret instruction inside func A. This ret instruction, as usual, will use the topmost D word inside the stack, which is currently this one, as a return address. So we are going to return to this location. This is basically what happens inside the stack. Some observations of what we have seen. At any point in the program, we are inside some function. This is just an idea of how we think about the program. The stack keeps the path to the current function, and we can use that information to return. Somehow the stack is our tool to find our way in the functions tree. Maybe just as a demonstration, let's take a look again at some state in the middle. Okay, let's go back to the beginning, and now let's try to get to some state in the middle, which is this, for example, and let's see what we have inside the stack. First we can see that we have two D words inside the stack, at least two meaningful D words. There are more D words inside the stack, but we don't really care about those D words. We only care about those two. These two D words are somehow a path to the beginning. they tell us the path that we have walked through. When we get, for example, to func C, we have a different path. And the depths inside the stack represent the length of our path. For example, when we come back here, our path is shorter because we are in func A, which is just one step from the start. However, when we were inside func C, for example, the path was of length 2 because the distance from the beginning was 2 calls. Let's try to simplify this. This is the functions tree that we have seen earlier, and this is a simple illustration of the stack. We begin from start. Then we move to func A, and we keep start inside the stack. We continue to func B, and we keep func A inside the stack. Now we want to go back, and we can do this because we kept func A inside the stack, so we just have to pop it. Next, we continue to func C, so we keep func A inside the stack. Now we want to go back, and we just pop from the stack. Finally, we want to return, and we do it using the last value on the stack, which is start. Another interesting observation. The value of ESP before the call instruction equals to the ESP after the ret instruction. This is true even if there are many calls in the middle. Another way to say it is that matching calls and rets leave the stack balanced. This is a pretty important subject. Before we wrap up, I want to share with you another illustration of running this kind of code. Some people find it easier to understand that way. This illustration is called the stairs illustration. We are going to look at the same code, but in a bit of a different way. We are going to have this picture, which is the stairs picture corresponding to this code. How should you interpret this picture? You can imagine it as having two axes. One, the horizontal one of time, and the vertical one of depth. What we see here is a description of the time we spent inside every function. Theoretically, we spent all of our time inside the start function, if we can even call it a function. But this is just an illustration. Then, after we called func A, we spent some time inside func A, and during this time, we called two other functions, func B and func C. Maybe as an example, whenever we spent time inside func B, we were at the same time inside func A and also inside start. Let's try to follow the code and see what happens. Our current location inside the code is going to be represented by this person. Maybe you can think about this person as yourself, if it helps you. So we are going to follow the execution of the code and see what happens to this person. We begin by calling func A. So we get inside the time domain of func A. Next we call func B. Then we execute some work inside func B, which means that we spend some time inside func B. And finally, we return. When we return, we get to func A, just before the call to func C. Next, we call func C. Then we spend some time inside func C. And finally, we return back to func A. just before returning. Then we return back to the start zone. This is basically what happens. I want to show it to you in a higher speed so that you can understand what happens here. I think that this is a pretty educating example of what functions are all about. Note that the depth corresponds to the amounts of elements currently occupied in the stack. Just as we have seen before that ESP goes deeper as we go deeper with the functions, the same goes here. The depth inside this picture corresponds to the amount of elements currently in the stack. Summary of this lesson. The call and ret instructions are just special purpose jumps. Call and ret allow us to call a function and return from a function call. Call pushes the return address to the stack, and ret pops the return address from the stack. The stack is a construct that helps us navigate the functions tree. At all times, it contains the full path to the current function, all the way from the beginning. Exercises. You will begin with the intro section, which contains explanations about local and anonymous labels, and also an example of stack balancing and checking that your stack is balanced. Next, as usual, there are the read code section and write code section. Good luck and have fun. See you next time.